In these two videos, we are not going to cover a huge amount of theory, but what we are going to do is just run through a few examples and a review of Lagrange's theorem, examples using cosets and examples applying Lagrange's theorem and some of its corollaries. So before we get started with Lagrange's theorem, let's do one more example with cosets, since it's often the case that students find this topic a little bit intimidating. So let's suppose, here's the question we're going to solve. Suppose that little g is an element that has order 14. So recall this means that g to the 14th power is the identity, and g to the k power, where k is a positive integer, less than 14 is not equal to the identity. If we suppose that g has order 14, let's go through and let's try and find the, let's say, left cosets of the group generated by g to the 7th and the group generated by g. I have left in parentheses here, although in general left cosets of a subgroup and right cosets of a subgroup are different. That is not the case when you're dealing with an abelian group. In an abelian group, the left cosets are equal to the right cosets. All of our work right here is going to be taking place in the group generated by little g, which is a cyclic group, in fact, very much abelian. So say left cosets, but really the argument would be identical for right cosets. And as we're dealing with an abelian group, specifying left or right cosets is a little redundant. So let's see here. We take the element, g to the 7th. Let's first figure out what the group generated by g to the 7th looks like. So we start taking powers of g to the 7th and figuring out what those elements are. So g to the 7th raised to the first power is one element that belongs to the group generated by g to the 7th. The next element we would put into the group generated by g to the 7th would be g to the 7th squared. And using rules of exponents, g to the 7th squared is g to the 14th. And what we're assuming is that g has order 14, and it follows that g to the 14th power is the identity. So we get to stop there. When we take a look at the group generated by g to the 7th, it's just the identity and the element g to the 7th power. So that's our subgroup, the identity g to the 7th power. The next thing that we're going to look at is the group generated by little g. And since g has order 14, we know that the group generated by g has the identity in it, and then it has g to the first power, g to the second power, g to the third power, and so on and so forth, all the way up until we get to g to the 13th power. As soon as we hit g to the 14th power, we'd cycle right back around to the identity. So to compute all of the left cosets of the group generated by g to the 7th inside g, we go through these 14 elements one by one, and we compute the set A times the group generated by g to the 7th, where A is one of these powers of g, the identity, g to the first, g squared, and so on. Now, in order to write down more simply what these cosets look like, we're going to use the rules of exponents again, and we go through just one at a time. So when we take a look at the identity times the group generated by g to the 7th, the coset that we get is just the subgroup, the identity, and g to the 7th power. When we take a look at g multiplied by the group generated by g to the 7th, the identity times g is just g. The g multiplied by g to the 7th power with rules of exponents is g to the 8th power. Continuing in this way, g squared multiplied by the identity is g squared times g to the 7th is g to the 9th, and so on and so forth. And we continue in this way until we get g to the 6th multiplied by the identity and g to the 6th multiplied by g to the 7th, giving us g to the 13th. By the time we would move on to g to the 7th, as it appears in the group generated by g, we would cycle back around and hit back to g to the 7th, g to the 14th. Remembering that g to the 14th is just the identity, we would cycle back around to this coset right here, and in fact so on and so forth. After we get past g to the 7th, we will have g to the 8th, g to the 9th, g to the 10th. Those all belong to a coset already, so there's no need to reconsider. So, all in all, when we look at the group generated by g to the 7th power and the group generated by g, we've got cosets of size 2, and we have 7 of them, which makes for a total of 14 things, which is the number of things in the group. Now, as you start working with cosets, one thing that you'll want to have a word for is the number of cosets that are formed when you're looking at subgroup H and the cosets of H inside of G. So we make the following definition. Suppose that G is a group and H is a subgroup, then the number of cosets of H and G, which is denoted with these cardinality signs and a little colon in between, G colon H, This is called the index of the subgroup H inside the group G, the index of H in G. And this is the number of cosets of H in G. This is an arbitrary definition. We've seen in examples before that even when G is an infinite group and H is an infinite subgroup, you can have infinite groups that have finite index. So this still makes sense even for infinite groups. But when we proceed to talk about LaGrange's theorem, this is really a theorem for finite groups. So let's suppose for now that we're dealing with a finite group G. We've seen before that each coset of H and G has the same size. Right? So in particular, if the subgroup is infinite, then all of the cosets are infinite. If the subgroup is finite, then all of the cosets have exactly the same size. And we've also seen that cosets are either totally disjoint from one another, or if you have two cosets that overlap at all, then they're exactly equal to one another. So cosets are either disjoint or entirely identical. And this allows us to count the number of elements in our finite group. So if we want to count the number of elements in our finite group, what we have is an argument right here. The index of H and G represents the number of cosets of H and G. So that's how many cosets we have, and each of them has size equal to the order of the subgroup, H, and this is really giving us a count of all of the things in the group. This holds because every element of the group belongs to some sort of coset, so we're definitely getting a count of at least the order of the group, and we're not getting too much because the cosets don't overlap, so we haven't overcounted when we count the number of cosets times the number of things in them. We haven't counted anything twice since cosets either are exactly equal or entirely disjoint. So we get this count. The order of the group is equal to the size of the subgroup times the index of the subgroup inside the group G, which is a very important and useful formula for us. And once you've sort of deduced this formula, you get the following theorem, which is called LaGrange's theorem and is hugely important in group theory. It says if G is a finite group and H is a subgroup of G, then the order of that subgroup divides the order of the group. So very important theorem. You should definitely know this theorem and its statement, have it memorized. One of the very important corollaries that we have of LaGrange's theorem is that if G is a finite group and little g is an element of that group, then the order of the element G divides the order of the group. This is an immediate consequence of LaGrange's theorem. If you take, since the order of this element is the size of the subgroup it generates, we get this corollary. But it's very important, just as it's hugely important to know the statement of LaGrange's theorem, it's also extremely important that you know that the converse of LaGrange's theorem is false. So what we have is that if you have a subgroup, then its order divides the order of the group. But just because you have a divisor of the order of a group, it does not need to be true that that group has a subgroup of order D, for D that divisor. And there's an important example of this, an easy example that we're going to go over, but the smallest example happens with the group A4. Now this is, remember, the alternating group on 4 letters, so the set of even permutations on 4 letters. There are exactly half of them, there's 12 of them. S4 has size 24, exactly half of the permutations in S4 are even, so A4 has size 12. 6 is a divisor of 12, and yet you can prove, and we will in the next set of slides, that A4 does not have a subgroup of order 6, even though 6 is a divisor of 12. So not 100% important that you know this specific example, but it's very important as you're working that you don't get confused into thinking that just because you have a divisor of the order of the group that you automatically have a subgroup of that order. It's not true, as we'll see in the next slides.